Swayam Prabha. Digital India. Educated India.
Today we will be talking about programming robots and microcontrollers. So, in the last class what we talked about is we looked at the various evolution of computer programming languages for robots mainly, that we saw that as robots started or as robots were first made in 1960s, that is the Puma robot, which was made by a Unimation company. So, the language that was used for programming the Puma robot was the VAL language, which is Victor's assembly language, and about 95% of robots in the world use VAL even today. And VAL has also evolved over VAL I, VAL II, that is essentially depending on how much interaction it has with the environment. So, today we will be looking at programming robots. We will take an example of controlling a Puma 6-axis 6-degree of freedom robot to perform a particular task. And then we will move on to programming microcontrollers, where you can actually build very simple robots using very cheap microcontrollers like mobile robots or ARM robots, and they are pretty good. Now, essentially what has happened is that the computer, which was very expensive about 1960s, has become much smaller in size, and it has become much cheaper. So, you can buy a pretty good microcontroller today like Arduino board, which has an Atmega 16 or 32 microcontroller at a very cheap price, and it is very good for controlling simple robots. So, that is the direction which we will see. First, we will start off with programming industrial robot using VAL II, then how to program a microcontroller using very simple languages which are openly available online these days. So, we will revise very quickly. So, in the last class what we looked at is that in VAL language we essentially have these commands. So, any VAL language program will consist of these 4 parts. The first is constants, variables, data objects, which are basically defining all the points in space. This is essentially for points in space where the robot has to go. The second is motion control commands, that is the robot has to move in space. Unlike an NC machine or a CNC machine, a robot essentially moves, and it moves from point to point. So, the second commands row of commands that are required are what we call the motion control commands, and then we have robot hand control, which is basically open close. So, to catch an object and to drop an object somewhere, the robot has to open its hand gripper and it has to close the gripper. So, that is what we mean by robot hand control. And then a robot will be interfaced with other machines. Okay. So, a robot is not going to work alone by itself. So, it will be interfaced with probably a material handling, it will be interfaced with NC machine or CNC machine, and then it will have to communicate with these machines. So, that communication is basically what is input output control, and as well as reading sensors. Okay. Different kind of sensors would be there, like force torque sensors, then we could have proximity sensors. So, how does a robot read such sensor information? Okay. And as in any computer programming language, we need logic, some kind of logic, and logic will need logical statements, like for example, if then else, it will read a subprogram, subroutine. So, that is what we covered in the last class. Today let us look at a specific program. Let us go through this very quickly. So, points are basically defined in space by giving the x, y, z and the 3 angles that the axis makes at that point. Okay. So, we define a point by giving a variable name. In this case it is P1, which says P1 is a point in space which has coordinates x, y, z, and the angles made is alpha, theta, alpha and gamma. Then we have move P1 and moves P1. So, we saw yesterday that if you want to move in a straight line, then we have to use a command called moves, and if you are not moving in a straight line, then we can use move, and this is more energy efficient. So, this is more energy efficient. This is a more energy efficient command. Then we have incremental commands like draw, approach P1 and depart. Approach P1 means approach the point P1 from the z direction and keep a distance of 50. This is basically used for catching an object and for picking up an object. So, when we are catching an object, unlike a human, the robot essentially has to go from the top. So, the robots go from the top and catch, and after catching it also lifts in a straight line upward. Okay. This is essentially to make it safe. Then we have there is hand control commands which are open close, and if you want to do immediately, open I and close I. So, this is open loop command, this is an open loop command, so it takes more time. This is a closed loop command, so this takes more time, this takes lesser time. Now, why would we need two different commands is essentially we have seen the case of a computer program, it executes line by line. So, what would happen is, suppose the robot hand is on top, okay, and we are saying open, and before when it is going down. So, suppose the hand is closed and we give the command open, it will ask the robot controller will the program will ask the robot controller to open, but as it is opening, it is taking some time. Now, when it is taking some time, if it has not fully opened, what would happen is as it is moving down, it is going to hit the object. So, we have to ensure that before it starts moving down, the hand should be fully open, okay, and that is what we say by open I. Now, when we are catching an object, exactly the same. Suppose the gripper is here and I say close. Now, as far as the program is considered, that line execution, as far as the program understands, if the line is executed, it is the task is finished, but it is not so. So, if I say close, it will slowly start closing, okay, it will take some time. Now, if I say close and then I also say move in the next line, so when it is closing, this will start moving up. So, what will happen is it will miss the object. So, in these conditions, we have to use close I and open I. So, close I essentially means that after it has closed fully, then only it will execute the next line. Okay. So, we need to be careful about this command and this command. So, one is open loop, the other is closed loop, and this is normally used for catching an object. So, or picking an object. So, picking an object, this closed loop command is used. Okay. Next, we have defined speed. We have also said that a robot can communicate by high and low signals. So, high here means 5 volts, low means 0 volts, and it can send different signals over different channels, and that is how it communicates. So, the basic command is if sig. So, signal means it is sending a signal or receiving a signal about a channel number, which is given here 2 and 3, plus and minus. Plus means high, okay, and minus means low. Okay. So, it is equivalent to 1 and 0. So, as far as logic is considered, that is how the robot interprets the plus and minus. Okay. So, the syntax is signal or sig, in short sig 2 and 3, then do something. For example, here it means wait signal minus 1 2. So, it means until the signal on line number 1 is minus and line number 2 is plus, it will wait. Okay. So, there are different logical statements also. Go to, this is clear, go to line number, go sub is a go subroutine, and then return. If then else is another logical statement. So, using these logical statements, we can write the program for the robot to perform different tasks. Then the robot can also read from ADCs and DACs. ADC is analog to digital converter. So, ADC 1 is equal to sensor 1 means whatever is coming on sensor channel number 1 will be assigned to ADC 1, and ADC 1 can be assigned to a variable which is 1. Okay. So, logical statements. DAC means digital to analog conversion, again the same logic is used. Now, today let us look at this program where we have a 6-axis robot. This is the Puma robot, which we will be seeing in the lab during the experiments of how it actually works and how we actually program it. So, this the task is to pick up objects from this pallet. So, we have a pallet here, and there are objects kept on the pallet. So, if I look at the top view of this, then this is my top view. So, this is my top view. So, what we can see is that there are objects here which are kept in a particular fashion, and the robot has to pick up one object at a time, take it from here and then drop it onto that cute point there. Okay. So, the task of this robot is essentially to pick up objects one at a time, to take it up and then drop it, go to the cute point and then drop it into that, and then come back and then come back, take the next one. So, now something that is very clear here is that you will require some kind of indexing. Now, what that basically means is the robot has to go to the first one, then it has to go to the second one, then the third one, fourth one, fifth one, in that order. So, you will need to do some kind of indexing here. Okay. The other is the robot has 6 degrees of freedom. The base coordinate, the base of the robot is given here. So, that is my 0 0 0. Okay. Now, in terms of the program, this point of the pallet here, the corner point which is given as corner, the coordinates of this is known. Okay. So, we define that the coordinates of this is known also. So, first thing is the coordinates of that point has to be known, because the robot moves from point to point in space. So, we have to define the coordinates with reference to the base of the robot, base is here. Next is height of the object is also known, height of object is known. Okay. So, these two things are given to us, the coordinates of this corner point is known and the height of the object is known. Now, if you look at the corner point, then the first object is here, which means it is at a distance of 20 along the x axis and minus 20 along the y axis. So, if this is my corner point, then the next point here is the center of the object, which is x 20 and y is minus 20. Then the other one is here. So, it goes by x is equal to 20 plus 50 and y is equal to, it remains as minus 20. So, when we are indexing, what is the logic in which we are going to write the program? First is we are going to write a main program, okay, which will have variables. Okay. Then we will have the motion control commands. So, variables first, then motion control, then we will have hand control, and after hand control we are going to have some kind of let us say we can call it a subprogram for indexing. Now, as you know that writing a program can be written in many different ways, and we are required to write a program in a very, very efficient way. Efficient means that first of all the program should be general, which means that if I change some parameters, the program should still work. Okay. For example, I have the palette here which has 4 by 3, it is 4 by 3 palette. Okay. So, there are 4 by 3 objects. Now, suppose I change the number of objects, the same program should be able to work. Okay. And that is the reason why a subprogram is written for indexing. So, suppose now I change the number of objects from 4 by 3, 4 cross 3 to 10 cross 5. Okay. Now, the same program simply by changing the number of rows and number of columns should still work. Okay. That is a good way of writing a program. A bad way of writing a program is the robot will start from here, go to the first object, pick it up, drop it into queue, come back, pick up the second object, drop it in the queue, pick up the third object, drop it in the queue, and the number of objects would depend on the number of lines you will have. So, if you have more number of objects, more number of lines. That is a bad way of writing a program, although that program would also work. Okay. So, a good way is write the program in a modular fashion. Okay. So, a very, very good way is modular fashion of modular way of writing a program, in which we define the number of objects in terms of variables, and if I change my variables, then the same program is going to work. The indexing I am going to do with a subprogram, so that every time if for the indexing the robot does not have to stay in the main program. Okay. So, what we will do is in the main program I am just going to keep these variables, motion control, hand control, then I am going to do the indexing in the subprogram. Okay. So, from the main program it will go to the subroutine or subprogram, do the indexing, come back. Okay. So, that is the logic. So, let us go over this again. My base is 0, 0, 0 here, the base of the robot. The objects are kept on this palette, the corner point of the palette is given, the coordinates are known. It is on the palette, the exact dimensions or the location of the object is also known. Okay. So, what the robot will do is it will first pick up the object from here, go and drop it in the queue, then it will index the first point to the next point, okay, next object top, then it will pick up the object, keep it there, okay, and then index it again, then go to the third one, pick it up and drop it there. Okay. So, the sequence of the writing the program is, I am given my corner, I know my corner point coordinate, I am going to first move this corner point to the top of the first object. Okay. Then I will pick up the first object, drop it there, then I will come back, index it. Indexing here means I am going to change the position of the center of this objects from the center of the first one, it will go to the second one, third one, fourth one, that is what I mean by indexing. Okay. So, that is the logic in which the program will be written. So, first of all let us see how the program is written. There is a sample. So, as we can see here that the remark is a remark statement which is not executed. Okay. So, the remark is corner and queue locations are taught. So, here it means the positions are known of the corner and queue are known. Okay. So, this is known, which means position orientations are known. So, the first thing that we write is we say max column, we define a variable as column, max column and max row. Okay. And I say my max number of column is 4 and my max row is 3. So, what we are doing here is we are defining a variable for number of rows and the number of columns of this. So, what is the advantage? If I simply change the number of rows and columns, I can handle a different number of objects. So, if I change the palette to a larger palette or a smaller palette, all I need to do is just change the number of rows and number of columns. Next is I want to start from the first row and the first column. So, I set row I to 1, sorry, row to 1 and column to 1, which means I start picking from the first object now. Then I set up a variable called pick, which has the coordinates of corner. So, I am defining a variable called pick. Now, this is the point that I am going to index on top of each object, and so that I can go and catch different objects. So, I am going to assign the coordinates of corner point to the pick point, okay. And then what do I do is I shift the pick point, by 20, minus 20 and 60. So, let us go back here and see what is done. So, this is my corner point, okay. Now, I assign another point called pick to the corner point. So, the coordinates of corner become the coordinates of pick now. Then what I do, I shift the pick point from here to the center of this object, which is 20 minus 20 and maybe it is 60. So, it is just on top of the object, okay. So, this is the coordinates of the point now, okay. So, this corner point which was assigned to pick has been shifted from here to the center of that object now. So, what it does first is I have shifted the pick and brought it to the top of the first object. Next what we do is we open I. Open I means open immediate. So, this is a closed loop command. After the gripper is opened with open I, what we do is move to the point pick, okay. Then it goes to point pick, and then this is the point pick, okay. So, this is my point pick now. So, it goes to the top somewhere here. So, that is my point pick, okay. In this view it will position somewhere here, my gripper is somewhere here now, okay. Let me draw it like this. So, just on top of the object my gripper is positioned like this now, and this is my pick point, okay. So, that is my pick point now. Okay. So, now after it has positioned there, what it will do is it will move down. So, draw is 0 0 25 sorry 0 0 minus 25, okay. So, we can notice that our z axis is positive in this direction. So, if I am going in that side, it is minus z, okay. So, what it does is after it has gone to the top of the object, so after it has gone here, we draw it and bring it down. So, it comes around the object. Now, it comes like that, the first object, okay. So, this is the command which is draw 0 0 minus 25. Then I close I. So, when we close I, it closes the gripper and catches the object. So, this one is for catching object, okay. After we catch the object, we move up by 0 0 plus 25. So, we go here and see after it has caught, again it goes this way to where it was. So, as I had explained that when we catch an object and we lift an object, then essentially we are moving down in straight lines along this z axis always. So, when we catch, we essentially go down like this. After catching, we lift also like this, okay. That is essentially for safety. So, after catching it, what it does, it moves to the point cute. So, the point cute has been defined already. So, it is here, okay. So, after going to the move point cute, what it will do, it will open the gripper and drop the object. So, it opens I and it drops the object. So, the first object has been picked up and has been dropped. Now, what it will do is it will go to a subprogram or a subroutine called palette, where it will do the indexing. So, after getting the first object, what it has to do, it has to index that point pick and bring it to the next object, okay. So, this what it does is it goes into a, so you can look at the command, it's go sub palette, and the program palette is here, the subroutine palette is program is given here. Now, in the palette program, what it does is it started off with the first row and the first column. So, it indexes the column with column plus 1. So, from the first object it comes to the second object, okay. But now it needs to check whether it has exceeded the number of columns or not, okay. So, it indexes, increases the number of columns by plus 1 and then checks whether it has exceeded the total number or not. If it has exceeded, it moves to row number 2, okay. So, this is the how the subprogram is written. So, it sets the column is equal to column plus 1, increases the number of columns. Then it checks if column is greater than max column, then 20. Now, 20 is here. So, go to 10, okay. Now, so if column is greater than max column, then 20, otherwise you shift pick by 50 0 0, okay. So, the program says that if the column is exceeded, so this 20 should come here, this 20 number is here actually, okay. So, if column is greater than max column, then 20, then go here, then set row is equal to row plus 1, okay. So, what it does is if the number of columns is exceeded 4, then it will go to the next column, it will go to the next row, okay. So, coming back here again, So, we are indexing from here to here, here to here, we are increasing number of columns. Now, after coming here, what would happen if it does +1, it will increase the it will exceed the number of columns. So, in that case it has to go to the next one, it goes here, okay, which is as shown here. Now, if the column is not exceeding, then what it will do, it will shift peak by 50 0 0. If you go back here, you see it was the peak point was here, so it shifted by 50, it has come to the next object now. Okay. So, this is 50 0 0, so it has come to the top of the next object. So, this has been picked. I want to go to the next object now, I am coming here now. Okay. So, that is what the indexing program does. Now, after doing this, it will go to 10. So, go to 10 means it will go back here to 10. So, move to pick, again the same thing, draw 0 0 minus 25, then close I means it catches the object, then goes up, okay, and drops it to the qt, and then again open I and comes back to palette again. So, this continues. So, this part will continue until it has picked up the 4 objects in the first row. Okay. Now, after it picks up the 4 objects in the first row, what will happen is, if the column is greater than max column, so once it comes here, it will become 4 plus 1, which will become 5. Now, 5 is more than the number of max columns, which is 4. So, what it will do, then go to 20. Now, 20 is this line number is 20. Then it will set the rows to row plus 1. So, it essentially means from the from this row it will come to this row, and then what it will do is, it is going to again check if the row is greater than max row. Max row was 3. So, if it has exceeded the max rows, it will basically go to 30, which is here, and then it will exit that program as and say that it has ended the program. Now, if the number of columns is less than, it is not greater than max row, then what it will do, it will shift the pick by minus 150, 50 and 0. So, from here it is going to shift the coordinates of pick to minus 150, 30 and 0, which is so, from here it comes to minus 150, minus 150 is right till here, and 30 is down here. So, it comes here. Okay. So, it comes to the center of the object there. So, after picking up this and this, it starts with this one, then again picks up this, then indexes, comes back here, this and checks, and then this is the way it is going to complete picking all the objects and then stop the program. So, this is essentially how the robot program is written to pick up a multiple number of objects. Now, here we can also add you can add sensor input output IOs, which is input output. We can add ADCs and DSCs. Okay. So, when we come to microcontroller, just after this I will be explaining what is ADC, DSC, and in a microcontroller how do you write that program. Okay. So, this is essentially to show a program written in VAL II. So, this was written in VAL II for an industrial robot like this Puma robot, which has 6 degrees of freedom. So, we are also going to do this experiment in the lab, where we actually have the robot, and we are going to see how that the robot actually works and how this program actually can activate a robot like this. Now, very briefly, where are the 6 degrees of freedom? There is 1 here, 1, 2, 3 is here, and 4, 5, 6 are here, 4, 5 and 6 are at the wrist. So, it is a 6 degree of freedom Puma robot, and this is a part of the lab. So, we will be looking at the lab also when we go to the lab. Okay. So, now let us move on. So, this is my Puma robot. So, now let us move on to okay, before we move on, one point that we need to look at is lead through teaching. Now, we have said that lot of tasks which involves, so tasks involving human skills, okay, are difficult to program. Why? Because you need coordinates of points in space. Okay. Now, it is very difficult to find the coordinates of points in space, because no sensor will give you x, y, z plus the angles. Okay. So, one way of teaching a robot is that a human being will actually teach the robot how to perform the task, which means that the human being is going to essentially perform the task, and when he is performing the task, we are going to record the position orientations of the end effector which he is holding, and then we are going to ask the robot to perform the same task. Example is here, for example, welding. So, in welding is an example. So, we have a human operator on one side, you can have a look at this figure, and there is a robot on the other side. So, what the human operator is doing is he is holding a joystick, and he is moving the joystick just the way he would move when he was doing welding. Okay. So, essentially when he is doing welding, whatever motions he is going to do, he is going to do with this joystick now. Now, when he is going to do the motions with the joystick, all the positions and orientations will get recorded in the memory of the computer, and then what it will do is the computer will then pass it on to the robot, and the robot will perform the same functions. Okay. So, this is what is called as lead through teaching, okay, and mainly tasks which require human skills. Welding is an example, assembly is another example, where some kind of human skill emulation is required. So, in such cases we can teach the robot through lead through teaching. So, let us next part where we would like to see how can you program very simple microcontrollers. Okay. Now, a robot program, this is an industrial robot is very expensive. Okay. So, a robot like this 6 degrees of freedom Puma robot would be about 50 lakhs if not more, and programming is done in VAL language, and they very often do not give you access to the controllers. So, how it is actually working, the control system inside, that is opaque. So, you will not know how the motion control is actually taking place. Okay. Whereas, if you make a robot yourself, which is very easy these days, essentially because microcontrollers are very cheap and they are very powerful. So, we can have a very simple a robot, we can make a very simple robot using a very low cost microcontroller, which is very good for understanding concepts of motion control, then control system, sensor input output, etc. So, in this course we will be looking at, one is in the labs we will look at programming the Puma robot, and then how can you build a robot yourself now. We have studied enough kinematics and we have studied control system, we have studied sensors. So, essentially putting all this together, how can you build a robot, a very simple robot, not an industrial robot, like a mobile robot which can move around and avoid obstacles. So, first thing that we will look at is mobile robot, how to make a mobile robot. Okay. Then we will look at a very simple arm, a simple arm robot, say 4 degrees of freedom, simple arm which can be controlled by a microcontroller. So, it can do pick and place applications, and then you can also interface it with vision these days. Okay. So, in order to do that, in order to get this far, what we need to do is to know kinematics. Okay. So, kinematics you have already studied, forward kinematics and inverse kinematics. Then we need to look at some kind of control, that also basic control we have studied, PD, PID. Then we need to look at sensors. So, sensors also, the different kind of sensors which are required we have studied. So, the sensors are like encoders. So, we have encoders, and then we have actuators like DC motors and servos. Okay. Now, something very recently and which are available are what we call servo motors. So, servo motors are already calibrated. So, you do not need to do any kind of control. So, servo motors already have a potentiometer, they already have a DC motor, and they have some kind of PID controller inside. Okay. So, all this coming together or bundled together is what we call a servo motor, and we can very easily control that using a microcontroller. And this has made life very easy for people trying to make simple robots, especially students, to do small experiments, because all you have is to take this package and plug it onto the microcontroller and do the experiments. Okay. So, let us move on. So, what we will be seeing in this now is we will see very basics of microcontrollers, only one type of microcontroller, then simple program for blinking an LED. Okay. So, we have an LED which we are going to blink, and just to get an understanding of how to program a microcontroller, then controlling DC motors, DC servos using the microcontroller, reading encoders, okay, to make the closed loop control system. So, this we will be seeing in this part on programming microcontrollers. Now, this is essentially done with a focus that you can do hands on experiments. Okay. So, the next part will be hands on experiments for us. So, you should be able to actually program and make this by yourself. Okay. That is the objective of this part of it. The theory part we have already covered, kinematics, control, sensors. Now, a microcontroller is basically a very small computer, okay, that consists of a memory, a processor and interfaces, okay, for input output. Okay. So, microcontroller can very basically be called a very small computer, and today it is very small, it is very cheap. Now, a microcontroller can be thought as a microprocessor which inbuilt peripherals. So, microprocessor plus input output and peripherals like memory, is a microcontroller basically. Okay. And microcontrollers today can be found in a variety of applications. For example, household applications like microwave oven, then your washing machine, okay, the refrigerator, TV sets, toys, then in cars, vehicles in cars, we have cars, the electronic stability of cars or the fuel injection, these are all controlled by microcontrollers. Now, microcontrollers have become very a part of everyday life, essentially because they are easy to program. This is something very interesting, that online open source codes are available today. All you need to do is to just download that open source codes, which are very easy to understand, and you can have your own program and you can have your own application. So, one is easy to program, the second is very cheap. Okay. So, a microcontroller would cost you, very good microcontroller like Arduino would cost you hardly about 700-800 rupees. So, they are cheap, they are easy to program, and they have a very wide range of functionalities. Okay. You can do so many things with a microcontroller, and because of this, microcontrollers are found everywhere today. Now, you would be familiar with MATLAB. MATLAB Simulink also has developed hardware interfaces for microcontrollers, where you can simply use Simulink. If you are familiar with how Simulink works, essentially you take the blocks, add together, and the blocks together is going to write the code. It will generate the code by itself, and you can download on the microcontroller. Okay. Now, there are different kinds of microcontrollers. For example, the Uno is one, Nano is there, Fio is there, Mimi, Pro, and so many others are there. So, in the market there are so many kinds of microcontrollers, and this is the Simulink table, which basically gives you details of how many input output lines are there. For example, digital input, digital output, then analog input, analog output, which is ADCs, then PWM, pulse width modulation, and then the other kind of input output facilities that it has. For each of the microcontrollers, it is listed here, and it also gives which pin number is doing what. So, for example, PWM is 3, 5, 6, 9, 10, 11 okay, for the Uno microcontroller. Okay. So, what we will be looking at is one particular kind of microcontroller, and we will be studying the Arduino microcontroller, and this Arduino basically is an open source hardware. Okay. So, it can be shown here. So, you can look at the, so it is an open source hardware which consists of the Atmel microcontroller, which is this one. So, this is my Atmel microcontroller. It is basically Atmega 16 or 32, and it is a programmable circuit board. So, this is my programmable circuit board. Okay. And it also has an easy to use software, which is the integrated development environment that runs on a computer. So, if you want to use this microcontroller, basically we have to download this IDE, which is openly available for Arduino, and then write the program in this, download it, and you can run your application. It is as simple as that. Okay. And the cost, as I said, the size is small, the cost is also very low. So, this Arduino hardware essentially consists of an Atmel microcontroller, and it is a programmable circuit board with easy to use software for integrated development environment. So, this is my software part, this is the hardware part. Okay. Now, if you look at the hardware part here, so this is the Arduino Uno R3. Okay. So, if you are looking at this, essentially this is my power. You can give the power from here. Then this is my, it can be connected to USB to connect it to the computer. So, what we need to do is to connect it with the computer, so that I can run this program on the computer and then download onto this one, okay, automatically. So, this is a USB connection. Now, these are the number of pins, these are the pin numbers. So, pin numbers we can see. So, you have pin numbers here, which are given here 1, 2, 3, 4, 5, 6, 7, 8 in that order. Okay. Then these are also analog pins. This is the analog in pin, which is A0, A1, A2, A3, A4, and each of these are the digital pins. Okay. So, you can see if you can see the writing clearly, this is Atmel, it is written here, and it is written Atmega 32 here. So, this is the microcontroller which is actually doing the processing. The others are some memory would be there, ADCs, ADCs would be there, okay, and digital IOs would be there. There are also interrupts, set, reset, ground, power, which is here. Okay. So, all of this made together is the Arduino Uno R3 microcontroller, which is very cheap, very easy to program. So, using this, what we will see now is how can we write a very simple program which is going to which ultimately can control a very simple robotic arm or a mobile robotic system. Now, to get that far, we need to understand two things. Number one is that there is a hardware, there is a software which is your IDE. So, the program will be written here in some standard language which is patented by Arduino itself, and then after you write the program you can download it. So, from here on the menu there is a download option where we can directly download onto this and then run the application. Okay. So, what you need one of this and you need this which is freely downloadable, this you need to buy. Okay. Now, now these are the pins of Arduino microcontroller. So, these are the various pins that are there, and you can see that there are digital pins, analog pins which are marked in respective colors, then we have power, then we have serial pins, then we have PWM which is pulse width modulation, and then we have interrupt pins. So, each of the color coding actually shows which pin is it and what is the pin number. So, when we write a program, what we are going to do essentially is we know which pin number is doing what. For example, if I am going to run a servo motor or a DC motor using PWM, then I know that I have to connect it to which pin number here. Okay. So, in the program I know which pin number is assigned for PWM, and I have to write the program accordingly. So, this very clearly gives us what are the pins and the pin numbers for a particular application what you are trying to do. Okay. So, now let us this is a very general figure. So, the operating voltage of Arduino is about 5 volts, okay, and the input voltage limits is about 6 volts to 20 volts. Okay. There are 14 digital IO pins. So, 14 of them, 6 of the digital IO pins are for PWM, pulse width modulation. Then now something to note here is that the current output from each of these pins is about 40 milliamperes. Now, 40 milliamperes is not enough to drive a DC motor normally. Okay. So, you might have to have some kind of a power amplifier here, power amplifier, okay, L298 kind of a power amplifier here. Why? Essentially because the current that is going out here is very, very small. Sometimes it is enough to drive a motor, okay, but larger motors it cannot drive. Now, it has a flash memory of 16 KB and it has EEPROM of 512 bytes, and the clock speed is 16 megahertz. So, 16 megahertz speed is pretty good these days for controlling a very simple robot, okay, for doing experiments and all that. Now, earlier days 16 megahertz was the speed of a computer, okay, as say about 2 decades ago. This was the speed of PCs and laptops, but today we are having microcontrollers which can give you that speed, and at a cost of say 600 or 700 rupees. And this is one of the reasons why microcontrollers are so popular with students in industries, in applications. Now, the simplified AVR architecture of the microcontroller is given here. We need not go into this in details. If you are interested, you can have a look what are the different parts. So, you have a CPU, and this is where the program runs. Then we have a RAM, you have EROM, you have timers, then there is an interrupt unit, and there are ports for input output. So, this is IO ports. Okay. This is the AVR architecture. Now, what we need to remember here is that we are coming into the programming details. How do you program a microcontroller like the Arduino microcontroller? So, here basically we have to communicate with the world. That means, I take sensor input or I give sensor output or I give output to the motors through pins. Okay. That means, the pin can be has a directionality. That means, the pin can be an input pin or it can be an output pin. So, the first thing that you need to do in a program is to port the pin data directionality, which means it is output or it is input. So, it is out or it is in, okay, that we have to specify. Now, input means when you want to take information from the external world, for example, you are reading information from a sensor, okay. It can be digital, it can be analog. When you are taking input from the world, from the external world, this is essentially called input, okay, and you are taking information into the machine control unit. The other is output. When you want to change the state of something outside the MCU, that means you want to turn on a motor or you want to turn off a motor. So, you are giving information out to the environment. Now, that would be called output. Okay. So, a pin can be input or it can be output. There are only 2 states. Now, by default, pin defaults to input direction on power up or reset. Okay. So, the default position is input, and you can program to change the directionality of the pin at any time. Okay. So, the first thing that we need to do, that is point number 1, is that I need to set the directionality of the pins, whether it is an input pin or it is an output pin, okay, which is next is microcontrollers that we have said are fundamentally digital devices. Okay. So, this is a digital device. Okay. So, the pin voltages are going to be digital, which means a high would mean a particular voltage and low would mean again a particular voltage. So, high or low basically means logic 1 or 0. So, high essentially means 1 and low means 0 in terms of logic. Okay. But in terms of the voltage that is generated is you have TTL logic is used, the transistor logic, which means that if TTL logic is being used, then 5 volts stands for high, which is 1, and 0 volts stands for low, which is 0. Okay. Because this microcontrollers are digital devices. Okay. And if you are using a CMOS, then high stands for 3.3 volts, which is 1, and 0 volt is low, which is 0. Okay. So, essentially high means 5 or 0 or 3.3, or so most common is this one. Okay. High and low essentially means these voltages. Now, what is the syntax? The syntax is very simple. So, pin mode is set up by this number. So, pin mode. Now, you'll see something which is very interesting here is that the language is English like. So, if you just read it, you understand that it is an English like command. So, pin mode essentially in English means what is the mode of the pin, and it simply says pin mode. Okay. So, pin mode first is the pin number. So, we are going to give a number here. So, what is the pin number and what is the mode? It is an input mode, it is an output mode. Okay. So, it is very simple command. Next is, so this sets the pin to either input or output pin. Next is digital read or digital write. Now, do you want to read or you want to write? Now, digital read can be high or low from a pin. So, it can be 1 or 0. Okay. Now, digital write would be you can write to a pin again, it can be high or low on a pin again 1 or 0. Okay. So, digital read simply says pin number, the syntax is digital read and a pin number here. Okay. So, that means it understands that you are reading whatever information is coming onto that pin. Digital write means pin number again and the value here. Okay. So, this means you are digitally writing to that pin and you are giving that particular value. Similarly, we can have analog read, again pin number, okay, and analog write. So, pin and value. Okay. Now, in case of analog value, because this is analog now and it is a digital device, so we have to break it up into 0 to 255 units. Okay. So, this is something different from here. Okay. So, here it is 0 or 1, but here it is 0 or 255, and because it is analog, we are dividing the full voltage range into 0 to 255. So, these are the main commands. Pin mode, we have to set the pin mode before we start. Digital read or digital write, depending on what we are trying to do in terms of digital data. And here, so this is in terms of digital data, this is in terms of analog data. Again, pin, if you are reading analog pin, just pin number here, and if you are going to analog write, then pin number and value. Okay. So, it is so simple that just by using these commands we can write a program, okay, and try and control different devices. Now, when we are controlling a motor, you would realize that we have a DC motor. Okay. If I draw a DC motor here, okay, so this is a DC motor. So, the input to the DC motor is a voltage, okay, but we understand that this microcontroller is a digital device. So, it cannot give a continuous analog voltage to drive a DC motor. So, what we do is essentially we do not give a continuous voltage. It is like saying if I connect a battery to this, okay, suppose this I am just showing here. So, if I connect a battery, then what would happen is this is getting a continuous analog voltage, okay, and it is going to and the motor will run, but I cannot give a continuous analog voltage because this is a digital device. So, there has to be some way of trying to give a my voltage. So, let us say this is a gear, this is another gear, and there is another link which is moving there. Okay. So, this is a gearbox, and this is my motor. I am going to give a voltage here. So, I am giving some plus and I am giving some minus here, okay, and the motor is rotating, the link is moving. Okay. Now, what I am saying here is that this one is analog, like if I connect a battery, it becomes analog. Okay, this is a battery, that is analog voltage. Now, I can't give an analog voltage using a microcontroller. So, what we do is we do a little bit of what should we say, a little bit of cheating, and then we divide this voltage or in a digital form such that I give waves. For example, this is what I do. Okay. So, if you want to give 5 volts as output, okay, so my total output is divided from 0 to 5 volts, this is my total. Now, suppose I want to divide this total range from 0 to 5, I want to give 2.5. So, what I will do is the output voltage is given in such a way by means of square waveform. So, if I look at this and this, okay. So, the frequency remains same, okay. So, if you can look here, if you see here, okay. So, the frequency has remained same. What has changed between this and this is the width of the wave has changed, okay. The frequency remains same, but the width is changing, okay. So, if I want to give more voltage, what would happen is I am going to increase the width of this, okay. So, more voltage means width is larger, okay. So, it is like saying that if I want to give 5 volts fully, then this fellow is going to become totally like that, okay. So, if it becomes totally like this, then the voltage is going to be 5. Okay. Now, if the width is half, okay, so the width is only half, then the voltage also will be half, okay. That is quite logical. If the voltage is 20%, sorry, if the width of this fellow is 20% of the full cycle, then what would happen is essentially the output voltage will be 1 volt. Okay. So, it is like saying that we are averaging this voltage, although this is a digital square waveform, what is coming at the output is an average of this, and the average you can see is 3.75, 2.5 and 1. So, as far as the device is seeing it, it is going to see some kind of a, it is equivalent to an analog voltage which is coming. Okay. And this is what we mean by pulse width modulation. So, a square wave with a fixed frequency, but variable on time, and the fraction of time signal is high, varies from 0 to 1 and is expressed as a percentage called the duty cycle. Okay. So, what is the duty cycle? So, the duty cycle is essentially the on time divided by off time. So, duty cycle is percentage of on time versus the total time. So, that is my duty cycle. And what is the output going to be? So, it is going to be duty cycle by 100 into the output voltage. So, this is going to be my output. So, this is my output. Okay. Okay. So, by doing this, by changing the duty cycle, what we can do is we can change the average voltage that is going out. So, it behaves like an analog system only. And next, so using this we can control a DC motor, I can change the voltage, right. Now, next what we are going to look at is we are going to see essentially the basic programming structure of Arduino basic structure for writing the program. And this is the basic structure. First, we have to define the global variables and include header files. Suppose we are doing serial input output, okay, or there are some standard header files, for example, controlling the servo motor. Okay. So, there are some standard programs which you can download and just use them instead of writing it yourself. Then we have a setup, void setup, this is the first part, and this is executed only once, this part is executed only once, and here we define the input output mode for digital pins. So, this is something we talked about. You have to define the mode of the pin, whether it is a read pin or it is a write pin. So, it is essentially read or it is write, and pin number. Okay. So, we define that and you define it only once. After that, we go into the next loop, which is this is an infinite loop. So, it will continue unless you stop it, and things like input from sensors, sending output, controlling motor, everything is done here. Okay. So, what we need to do is to set my pins, input output pins. Then what we need to do is to write our program what we want to do, what is the task. Okay. Then what we can do is we can go back to the developmental software, which is here. So, we go back here. Okay. So, this is my IDE. In the IDE there is a download. So, we can simply take this and download it onto the microcontroller, and the moment it goes onto the memory of the microcontroller, it starts operating. Okay. So, most of these examples we are going to do in the lab. So, this is a theory of the examples, and the actual experiment will be done in the labs. Okay. Now, for example, this is a very simple program for blinking. Okay. Almost everybody starts off with this. So, there is an LED. So, for example, there is an LED here, and you can blink this LED. Blink means on off, on off, on off. How do we start? First thing is we write our pin mode. So, this is pin number 13, and this is an output. Okay. Now, I need to define my there is an LED. This LED is a built-in LED. Okay. This is LED built-in. So, I am defining my built-in LED to be number 13, that has to be defined. Okay. So, pin mode 13 is output. So, this is an output pin. So, I have defined my pin. Next is I am going to write my loop, okay, the whatever I want to do. So, I want to blink this LED in a particular sequence. So, I am going to digitally write LED built in, which is number 13, high means 1. Okay. Then I will delay, means it will be on and wait for 1000 milliseconds. Then I will say again digital write. So, LED built in, which is channel number 13 or pin number 13, and low, which is 0. Okay. So, this would mean 5 volts, this will mean 0 volts. Okay. So, this is a very simple program, extremely simple. You can see how simple it is. So, high would mean 1, which corresponds to 5 volt, and this corresponds to 0, corresponds to 0 volt. Okay. So, you can see this is an infinite loop. So, this loop will continue because it is an infinite loop. Okay. So, you just download the program and the LED will start blinking on and off, and you can change the delay time here, the delay time here. Okay. So, this is essentially to show how simple it is to write a program using this Arduino microcontroller with the IDE, and you can use it for different applications. This is another application where we have 2 color LED glowing. Okay. So, in the previous case we had one LED, and that LED was the one which is inbuilt in the microcontroller. So, some of them are inbuilt in the microcontroller, some of them are not. If they are not, then what you can do is you can take an LED and plug it into particular number of pins, particular pins, which is the output pin. This is a program for 2 LEDs, okay, which are glowing. Slowly it will increase and slowly it will go down. So, there are 2, maybe a red and a blue. So, red and a blue LED. Okay. What will happen is it will slowly go up, and this will slowly come down, and then it will reverse cycle, this will come down and that will go up. Okay. This is what we mean by glowing. Okay. So, the program you can see, we are first defining the red pin as pin number 11, blue pin as pin number 10, and then we are giving the red pin mode. Red pin is output, blue pin is also output, because we are giving output, we are not taking any input here. Okay. Then what we are doing is we are going on to write the program in which there are 2 loops, this is 1 and this is 1. So, this is one of them will increase and one of them will decrease, right, and then we can also print serial print in, we can print this onto the computer. Okay. So, this is another program which is the commands are the same. So, analog write, it says 11, okay. 11 is the pin number and gives the value. Now, the value is coming from here. So, value 255 is the highest value. Okay. So, it gives the full voltage. So, this is the way the program works. Now, sensors interfacing. Now, sensors usually have 3 terminals. We have the voltage, ground, and the signal, either digital or analog, and this is an example of Hall effect sensor. So, we have studied about Hall effect sensors. So, these are basically magnetic sensors. So, how Hall effect sensor works is essentially this is a magnet north south, and we have a Hall effect sensor here. So, normally the magnetic lines of force will be going like this. Okay. Now, if an object comes in front here, what will happen? The magnetic lines of force will go like that. So, essentially the magnetic lines of force pass through this or does not pass through this is checked by the Hall effect sensor. Okay. And either it gives a 0. So, this will give 1, that will give 0, okay, reading. And what we have done here is again we have connected the LED to line number 13, the sensor is connected to line number 3. Now, this is an input and LED is an output. Okay. So, this is my LED, I have connected my Hall effect sensor here to channel number 13, which is connected here. Okay. And this is the power, this is simply going for the power, and LED is the internal LED which is blinking there. Okay. So, sensor is just one sensor input is coming here, and LED is internal. Okay. Now, here we are first defining the pin mode as the LED, and output pin mode is 13 from here, and this is an output pin. Okay. The LED is an output pin. Now, pin mode sensor is an input pin which is coming from the Hall effect sensor. Now, again we are writing the value which is coming is equal to the digital read from the sensor. So, it is reading the sensor, Hall effect sensor. So, it is a 1 or it is a high or a low. So, this is high or a low. Okay. And then in case it is high, what it will do is it is going to make the LED blink. Okay. It will make the LED on. Okay. So, if the input which is coming from the sensor is high, the LED will start glowing. Now, if the input from the LED is low, okay, what will happen is if the input from the Hall effect sensor is low, what it will do is it will digital write LED as low. So, this means LED will go off. So, whenever you bring something here, how this works, this is my Hall effect sensor. So, suppose we have a wheel, this is an experiment which we will be doing. So, suppose we have a wheel and it has a cut. So, this is my wheel and it is rotating about that axis. Okay. This wheel is rotating. So, whenever this cut comes, what would happen is this will go off, and whenever the wheel is there, this will come on. Okay. So, it is measuring the rotation, number of rotations of this wheel. Okay. So, this is not a very good example. Let us take another better example. So, we have a wheel, and on the wheel I have put a projection like this. So, whenever the projection comes in front of the Hall effect sensor, it will show 1. Okay. The moment this projection goes off somewhere else, it will show 0. Okay. So, whenever this comes in front of this Hall effect sensor, the LED will blink. Whenever this is gone, what will happen is the LED will also go off. So, this is a very simple program to actually show that how to use a Hall effect sensor and measure the rotation. So, this is exactly how an encoder, this is exactly similar to how an encoder works. Okay. Now, motor interfacing. Now, motor interfacing is done this way. Something to remember here is that the Arduino can only provide 40 milliamperes. Now, if it can provide 40 milliamperes, this is not enough to drive a motor. Okay. So, we have to use a H bridge power amplifier, which is essentially going to amplify the current to up to 600 milliamperes. Okay. There are different H bridges which are available, L293, L298, these are all H bridges which are available. So, how do we run a motor? So, this is a DC interfacing for a DC motor. So, this is my L298, this is my power amplifier. Okay. This power amplifier is connected to this number of pins. Okay. And yeah, so this is a power supply which is going to the power amplifier. This is my DC motor. So, this is my plus minus of my DC motor. So, this is the DC motor plus minus. Now, what we are doing here is that we are taking the output from here from the Arduino and then giving it to the power amplifier. From the power amplifier, the power is going in there, and to control how much is going to go in, we basically have a potentiometer. Okay. So, by rotating this potentiometer, you can actually control how much voltage is going to go into this into the DC motor. So, if you are controlling, what are you controlling here? So, we are controlling the voltage to motor by rotating this potentiometer. So, by rotating the potentiometer, we are able to control whatever voltage is going. So, if you are controlling the voltage to the motor, then you are controlling the speed of the motor. Okay. So, this is how you can control the speed of a motor. Now, there are other kinds of motors which are called servo motors, which are very common these days and very popular with students. Now, the servo motors essentially consist of a DC motor as one package. So, this is one full package. So, there is a DC motor here, there is a potentiometer, and there is a gear, and this is my link. Okay. Now, the advantage of this is that there is a control circuit built inside there. So, there is a PID kind of a controller here, okay, and this is calibrated. So, what do I mean by calibrated is that the potentiometer is calibrated to move this from 0 degrees to 180 degrees, okay, or from 0 degrees to 270 degrees. Okay. So, it is pre-calibrated from before. So, what it basically means is that I can give a particular voltage. So, let us look here. So, this is my calibration that is normally there. So, by changing the pulse width in PWM. So, by using the PWM and changing the pulse width, what we can do is we can position the motor at a particular angle. So, this is showing that this is showing 180 degree position, this is showing 0 degree position, okay, and this is showing neutral position which is there, which is 90 degree. So, 0, this is 90 degrees, and this is 180 degrees, and each of this corresponds to a pulse width. So, if this is my full pulse, then this is corresponding to 90 degrees, this fellow is corresponding to 0 degrees, and this is corresponding to 180 degrees. So, this is my full pulse. Okay. So, by changing the pulse width, I can position the motor. It is pre-calibrated that way, and essentially because there is a potentiometer there and there is a control structure, a control circuit right inside only. Okay. So, what we can very easily do with this motor is, this is a servo motor interfacing from library. So, this is a servo.h. Okay. So, this is already a program which has the internal details of the servo motors and the calibration part of it. All we need to do is to now assign the pins, and then to drive and to vary the. So, what we need to do here is to vary the pulse width. Okay. So, what this program is doing is, it is showing position. It starts off with position equal to 0. Okay. So, this is the variable, and what it is doing is position equal to 0 to position less than equal to 180 degrees is incrementing by 1 degree, okay, in steps. So, what this program is doing is it is using the servo.h, which is already a header file here, okay, which has all the internal details, and in this case it is starting, this for loop is starting with 0, then it's incrementing this by 1 unit, and what is happening is the stepper motor will start moving, sorry, the servo motor will start moving from 0. So, if it was here, this is my 0, it will move in 1 degrees and come till here, this is 180. Okay. So, this is writing a program using a standard header file. Now, we can also write a program from scratch, okay, in which case we have to assign the digital write pins, okay, then the digital read pins, okay, sorry, digital write, and then depending on the pulse width, I can actually control the motor at a particular angle. So, this is an example of writing a program without using the header file, where you are simply using the pin mode, digital write, digital read, and controlling this motor to go from one point to another. So, we stop with this today, and from the next class we will be moving on for experimental details, and where we are going to do all these experiments and to see how you can use a servo motor to build a small simple robot arm. Okay. So, we stop here today. Thank you.